Okay, hello everyone, and welcome back to my YouTube channel and my classes about power system analysis. Today we have a practical session about power system transient stability. To be honest, it's mainly application of the equal area criterion. Okay. However, I would like to start this video making a comment for all the viewers, okay, and all my students. Um, Basically, when you are studying power angle transient stability and also the equal area criterion, there is no possibility that you can do the possible all the possible cases that you can find in real life. I mean, there are so many combinations of changing factors and things that is almost impossible that you can cover all the exercises and all the examples to cover every single possible situation. Okay, for that reason, what I suggest to my student is, instead of trying to solve many exercises, they must understand the basic, they must understand the theory, they must understand the physics behind the problem and the solution, of course, and from there they will be able to overcome any kind of situations that is coming in front of them. Okay, for instance, this is the example 4.1, and it's totally different to anything that is in other books. Okay, in other books you will find that the classical disturbance is increase the mechanical power. Okay, we move the mechanical power from here to there. Please determine the new if the system is stable, for instance. That is the classical question. Here I am afraid that I don't like the classical question. I try to go for something that it could be challenging for my students, that they can use the brain, the magnificent intelligence that they have. Okay, well, let's go for business. Here we have, let's consider the 60 Hz three-phase system that is shown below. Okay, it's a very basic power system. There is a synchronous generator here, a step-up transformer going to two transmission lines in parallel, and then we are going to an infinite bus bar. Okay, this is a classical example of single machine connect to an infinity bus bar. Okay, here we can recognize that we are working with a synchronous generator. The inertia constant is 0.45 megajoule MVA, and the transient reactance is 0.2 per unit. Okay, the synchronous generator is connected to the infinity bus bar using a transmission system. Okay, in this case, this is purely reactive transmission system. What I am telling you over there is they are not resistance, there is no active power losses. All the active power produced here is reaching the infinity bus bar. Okay, then they say the reactants are marked in the single line diagram, and all of them are given in a common base. Okay, what I'm trying to say is you don't need to make any base changes over here. Okay, you need to focus on what is important, and this case is transient stability. Then there is some data from the load flow. The generators deliver an active power of 0.6 per unit, power factor of 0.8, lagging power factor, to the infinity bus bar when the voltage at the infinity bus bar is 1 per unit. Okay, some of my students, they are confused. Okay, where is that? Well, what this telling you is that power is here. Okay, in terms of active power 0.6 will be the same here to there, because they are not resistance in the middle, they are not active power losses. All the active power coming from here will go there. Okay, it's clear, simple. All my students can see that. But the reactive power is a bit different. Okay, this problem is giving you the power factor here, 0.8 lagging power factor, because the reactive power here is different to the reactive power here. The reactive power here, you have many losses cross the transmission line, the transformer. That means that the reactive power that you send here is not the same reactive power that is arriving there. Okay, take in account that. Okay, power factor is given there. and also the active power is given there, okay? And also this beautiful infinity bus bar is working at 1 per unit. Now there is a question, okay? Assume that a disturbance is inserted at t equals 0 seconds, okay? T equals 0, something happened. And this disturbance is happening is a sudden decrease in the mechanical power, okay? And as you can read over there, there is a sudden decrease of the mechanical power of 10%, okay? 10% is the power reduction, okay? And that is coming from the previous value from steady state. What I'm trying to tell you at this moment, is that the power, the original mechanical power is P mech 0, but there is a reduction delta per mechanical power, and that is 0.1 times or 10% of the original power, okay? Now the two interesting questions here is, first, determine if the system is stable. I mean, can this system survive this kind of disturbance? And assuming that the system is able to survive this disturbance, indicate what is the final operating angle in a stable state, okay? Two couple of questions over there, very simple problem. Let's start with the solution, okay? Well, what you need to understand is this is the condition previous to the fault, okay? We have the generator, transformer, two transmission line going to the infinitive bus bar, okay? And then we have some load conditions, okay? Some load conditions. But before going to the load condition, this is the reactance, this is the reactance diagram, okay? This is the reactance diagram previous to any disturbance, okay? This is the condition, this is the starting condition. The system is working in a steady state. We have here the transformer, we have here the transient reactance, two transmission lines in parallel, and we are going to the infinitive bus bar, okay? And now what we need to do is that previous to any fault, this generator is delivering power to this infinity bus bar, and the active power that we are delivering over here is 0.6, okay? That is coming from the problem statement. And here the voltage is 1 per unit. All of you know that the voltage is 1 per unit. And the power factor, I already explained, the power factor is measured here, and it's 0.8 lagging power factor, okay? What we need to do now is, okay, let's see the let's evaluate, let's assess the steady state condition previous to the fault, okay? It's very simple. What we need to do is, this is the impedance diagram. You can see here again the impedance diagram, and it's clear for you that the power factor and the electrical power, the active electrical power, is delivered here. As I say to you, I'm not considering any reactive power for this kind of power system stability, okay? Reactive power is not concern of transient angle stability. It's active power the main concern, okay? What I want to do now here is, I would like to know what is the apparent power that this generator is delivering to the infinity bus bar, okay? And it's extremely simple, because all of you know something about power, and all of you must realize that the active power divided by the power factor, the active power divided by the power factor, that define the apparent power, okay? 0.6 per unit divided by 0.8 power factor, and here what we have is the power factor, okay? The angle that define the power factor in this case is 0.8 the power factor, and we obtain that the power angle is 36.86. What I'm telling you is that now we know the apparent power that it is reaching here, the infinitive bus bar. Okay, but that apparent power is creating some current moving through the circuit. Okay, and it's very simple to calculate the current. Okay, because all of my students, they are quite clever in apparent power divided by the current, by the voltage. You must notice that here we have the conjugate, because you must remember the equation for apparent power, and in the denominator we have the voltage. But this is the voltage of the infinity bus bar. Okay, this is the voltage at the infinity bus bar, that is 1 per unit. Okay, it's already given, is 1 per unit. Let me move a bit here, and we are assuming that this voltage is reference. As this voltage is reference, the angle is 0 degree, and from there we can obtain, this is the current, that is the phasor representing the current in that system. Okay, what is the next step? Well, the next step is quite interesting, because what we need to do now is to calculate what is the impedance that is defining the power flow between the generator and the infinity bus bar. Okay, now what I will do is very simple. We are in previous to the four conditions. You are there with me. Okay, you can see over here, and I put below the equations, the reactance diagram. Okay, what I want to know is what is the impedance that is connecting those 2 points. Okay, and it's very simple for you. Circuit analysis, those devices are in series and then connected in series with the parallel between those things. What I'm trying to say is that the total impedance interconnecting the generator and the internal voltage of the generator and the infinity bus bar is the transient reactance plus the transformer reactance plus the parallel of the 2 lines. Okay, and here we get the result. That is what I was looking for, this 0.475 per unit. That is the reactance. That is defining the power flow that is moving from the generator to the infinity bus bar. Okay, what is the next step? Well, very simple. Now we know impedance, now we know currents, now we know power flow. The next step is to calculate the internal voltage of the generator. Okay, we are using the letter E, and in this case it's very simple. We can apply Kirchhoff voltage law. Kirchhoff voltage law for the generator, and using Kirchhoff voltage law is very simple, that you can say that the internal voltage is the terminal voltage plus the voltage drop across the transmission system plus the voltage, okay, at the infinity bus bar. Okay, this is the voltage at the infinity bus bar. Okay, you can see that from here. What I am telling you is that this voltage over here, the current is moving here, yes, and this is the voltage at the infinity bus bar. Okay, what I am doing is Kirchhoff voltage law here, this voltage drop plus this voltage drop plus this is the equivalent reactance between the generator, internal voltage of the generator and the infinity bus bar, multiplied by the current, and then plus the voltage drop across the infinity bus bar. Okay, very simple. You put the number together over there and you get the internal voltage. Okay, here I would like to make a short remark. Okay, it's a good idea that you plot over there your phasor diagram, and in your phasor diagram you can get some useful information. What you need to understand is that the angle between the internal voltage of the generator and the infinity bus bar, that is the angle defining the power flow. Okay, in this case, from that phasor diagram, because the infinity bus bar is located at reference, it's simple to see that the initial angle, operating angle of this machine is basically 13.21. Okay, Very simple. Next step. The next step is I must define the equation that establish what is the power, the active power flow between the generator, the internal voltage of the generator, at the infinity bus bar, okay? What I am telling you is that I need to define this equation because this is the power angle equation, and the power angle equation will tell me what is the maximum power transfer that I can have between the infinity bus bar and the internal voltage of this generator, okay? When you put the number together, you obtain here is quite important. You can see here, this is the equation defining the pre-fault power angle condition, okay? Well, what is the next step? Well, the next step is we already have all the pre-fault conditions. We are perfect about pre-fault conditions. The next step is, okay, let's study what is the situation when we have the disturbance, okay? In this case, all of you can see, in this case, we have a disturbance. In this case, the disturbance is a sudden and a step reduction on the mechanical power, okay? What I am telling you is that we have this machine operating. We have an initial mechanical power here. The initial mechanical power is equal to the initial electrical power, 0.6 per unit. And then we have a reduction of 10%. 10% of 0.6, all my students, they are extremely clever, is 0.06 per unit. That means that the mechanical power will move from 0.6 to 0.54, okay? That is this. We are here initially, this is the initial operating point, and then there is a sudden reduction on the mechanical power. What we want to know is this system will be able to support, to overcome this kind of disturbance, okay? Okay, and what you need to understand, and this is the important part, all my students, they must understand that we are here, we are at point A. We are at point A, okay? And when we reduce the mechanical power, what is happening, we reduce the mechanical power, what is happening is in this region, the electrical power is bigger than the mechanical power. I'm sorry. The electrical power is bigger than the mechanical power, okay? And because that situation, what will happen is that the machine will deaccelerate, okay? The machine will reduce the speed and start to reduce the speed and going down. Let me amplify this, okay? Hopefully this will work, okay? Okay, we are in point A. We'll reduce the mechanical power to here, and the machine start to reduce the speed, and this is the accelerating process. But when the machine reach number 2, when the generator reach the letter B, the point B, there is a problem because the machine is already so slow, and it will reach point C, okay? The point C is the minimum oscillation that this machine can reach in this case. And there, I don't know if you realize, but between B and C, mechanical power is bigger than the electrical power, okay? And in that region over here, the area 2, in that case, the machine will say, okay, mechanical power is bigger than electrical. For that reason, the machine will start to accelerate, and they will try to come back again to B. But again, you overcome, and the situation will be like this. We start from A, and the machine will oscillate, and if everything is fine, we will stop here operating at B, okay? Okay. Now, what is the situation? The situation is that you must understand this is the original operating point. This is the starting point of everything. And the mechanical power of the point B is already defined. It must be clear for all my students that the point B is already defined. Okay? And because the point B is already defined, I don't know if you realize, but the area A1 is a number. It's constant. But what is not constant is this point location C. Okay? What you need to do is the following. Because the power reduction is from A to B, the point B defines the angle delta 1. The angle delta 1 is basically and very simple to calculate. All my students, they are so clever that they can calculate the angle delta 1. And the angle delta 1 is very simple because you will use this equation over here, that is 2.62 sine of delta 1, and from there you will extract delta 1 because it's equal to 0.54, and that is the final mechanical power. Okay? Well, you can obtain here, you can put the numbers, and the angle delta 1 will be 11 degrees. Okay? That is all. That is very simple. What is the next step? Well, the next step is that we want to know, and that is the classical problem that we need to solve here. What we need to do is the following, okay? What we need to do here is we need to apply the equal area criteria, okay? But the equal area criteria must be applied in order to identify what is this oscillating point, okay? We want to know what is delta max. And to do so is very simple. We know a lot of mathematics. We need to define what is the area A1. The area A1 is calculated between delta 1 and delta 0, and is basically the difference between the electrical power and the mechanical power. Very simple, as I say to you, this is a constant area, this is a number, and here you got the demonstration. When we put the number together, that area is 0.00070, okay? But the other area is probably the quite interesting one, because if we know this area, now this area is the unknown area, because this mechanical power is what we want to know. We want to know how much is this mechanical power, because if you move if you move down, you increase the area, but if you move up, you decrease the area. What I'm trying to say is right now the second area, that is the accelerating area, is basically an integral going from the delta max to delta 1, okay? And below you will find the mechanical power, and on the top you will have the electrical power, okay? This is the good one. This is the good one because this is the variable that we are looking for. We are trying to obtain, we need to calculate that delta max, okay? And because delta max is the only one that we don't know, well, when we solve that equation, look over there, the area A2 is basically an equation. But it's a very interesting equation. It's a non-linear equation. Why is non-linear equation? Because you can see here, this is the variable that I am interested, that is delta max, but also delta max is inside this cosine. That means that is a very ugly non-linear equation, okay? What is the next step? Okay, the next step is applying the stability criterion, the equal area stability criterion, and what I am doing is I am equalizing the area 1 with the area 2, and equalizing the area 1 with the area 2 is similar to running the difference between those. And here we have this beautiful nonlinear equation, okay? We have a nonlinear equation because it's combining the delta, the angle delta, is combined with the cosine of the delta angle, okay? That is great. That is great, okay? And now what you need to do is basic mathematics, okay? If you want to use MATLAB, if you want to use any numerical method that you feel is your favorite, and it's a mathematical method to solve problems, nonlinear equations, please feel free to use it, okay? If you use any numerical method, you will obtain the value of delta max, okay? And delta max over there, you can see that the solution is 10.5 degree, okay? As you can see, we obtain an angle. That angle is delta max. And we need to be sure that that angle is a possible solution, okay? If we go back here, we are starting from 13 degrees. The final operating angle must be 11, and the maximum oscillation is reaching 10.5. That means that is a real solution, is a number that is feasible, because the solution must be in between 0 and delta 1, okay? And this solution satisfies that condition. This solution delta max is between 0 and delta 1, and it's a proper solution, okay? What is the conclusion here? Well, there are a couple conclusions. First, this system is able to survive. This system is able to absorb this disturbance. The system will be stable in terms of transient angle stability. The synchronous generator will survive this disturbance, and the machine will stay synchronized to the power system, okay? That is the case of a sudden decrease of 10% of the mechanical input, okay? And what we need to understand here is that the power angle will oscillate, and the maximum oscillation will be reaching 10.53 degrees, okay? But the final operating point will be 11.87. What I'm trying to say is 10.5, it will be the maximum oscillation, but the final operating point will be 11.87. Okay? Well, thank you very much for attending to this class, and thank you very much for watching the videos. Thank you.